Okay, so torque isn't a force. It's not a force. When people say torque is a force, it's not a force. You've got to be careful with how you word things, because in engineering, you word things wrong, shit goes wrong, you know, your ass is on the firing line.
Get the fuck out of here, you're fired.
So, and you know what's weird is that there are other people out there on YouTube who aren't as passionate, and you could say passionate, you could say pedantic.
What, like anal?
I would prefer the word passionate, because as engineers we understand terminology, we understand that strength is different to toughness, that's different to malleability, to ductile, to tensile, to compression. All of these words, something's tough, brittle, strong, hard, they're all different. So, torque is a vector quantity. It's a vector quantity. Here's the axis. There it is. Axis. I can't even write. That's because I broke up for summer now and school's out. Axis. Okay, now imagine, let's come off this at 90. There we go. That there. We are at 90 degrees. Okay. Torque is a vector quantity, and I'm going to keep saying that. It's a vector quantity. It's also a measure. Torque is also a measure of. None of them say force. So if we apply a force, we can apply a force, and we'll apply a force up, straight up, 90 degrees again. We'll apply a force, doesn't matter what it is. So torque is a measure of the force that can cause the object to rotate about the axes. So I'll say that again. Torque is a measure of a force that causes an object to rotate about an axis. So acceleration, angular acceleration. So our movement is rotational. Our acceleration is rotational. Our acceleration is angular. Everything about this is to do with theta. Okay, if we're applying a force there, okay, we can assume safely the direction of the vector, of the torque vector, about the axis. If we apply the force in this direction, it's obviously the opposite.
They've done studies, you know.
X minus, X plus, whatever you want to call it. Okay, so torque is a vector quantity. It's a measurement of the force that can cause an object to rotate about an axis. Torque is a vector quantity. So the direction of the torque vector depends on the direction of the force on the axes. All right? So anyone who has ever opened a door has an intuitive understanding of torque. So when a person opens a door, they push on the side that's furthest from the hinge. So pushing on the side that's closest to the hinge would require considerably more force. The work done would be the same in both cases, but the larger force would be applied over a smaller distance if you were to open the door nearer the hinge. People generally prefer to apply less force, hence the usual location of the door handle is said distance from the hinge. So the other thing about torque is it can be static or dynamic. And not to confuse things, it's not really confusing at all, but a static torque is one which doesn't produce an angular acceleration. So we can still have torque applied without any angular acceleration. So somebody pushing on a closed door, for example, let's just say it's not locked, forget the lock, but if it's a closed door and it's rigid, if we apply a static torque to the door, or a torque to the door, it's a static torque because the door isn't rotating about its hinge, despite the force I'm applying. Someone pedaling a bicycle at constant speed is also applying a static torque. Constant speed, not accelerating, static torque.
At the moment, I'm afraid it's a forlorn look to Gomez, the Colombian.
Right. The drive shaft in a car, obviously accelerating off the start line. Is obviously carrying dynamic torque because it must be producing an angular acceleration of the wheels, given the car is accelerating along the track. Okay. The terminology used when we describe torque, depending on who you're talking to, and it can be confusing, which is why it gets a bit confusing. Engineers sometimes use the term moment or moment of force, and we use those interchangeably with torque. So the radius at which the force acts is sometimes called the moment arm, because it's obviously a moment of force. Clockwise, counterclockwise. So to measure torque, the magnitude of the torque vector tau for torque, is given as tau is equal to F times R sine theta. So tau is equal to F times R sine theta. So R is the length of the moment arm, and theta is the angle between the force vector and the moment arm. So in the case of the door, the force is at right angles, which is 90 degrees to the moment arm. So the sine term becomes 1, because sine theta sine 90 degrees is equal to 1. So we therefore say tau is equal to F times R, force times radius. So the direction of the torque vector is found by convention using the right hand grip rule. So if a hand is curled around the axis of rotation with the fingers pointing in the direction of the force, then the torque vector points in the direction of the thumb. And that's a common way of showing that. So, and how torque is measured? Well, the standard unit for torque is Newton meter. In imperial units, they use foot pound. This can be confusing though, because colloquially the pound is sometimes used as a unit of mass, and sometimes as force. But what is meant here is pound force. So the force due to Earth gravity on a 1 pound object. So the magnitude of these units is often similar. So 1 Newton meter, broadly 1.74 foot pounds. Measuring a static torque in a non-rotating system is usually quite easy and done by measuring a force. Given the length of the moment arm, the torque can then be found directly. As just described, measuring torque in a rotating system is considerably more difficult. So how can we increase or decrease torque? How does that happen? Well, it's sort of often necessary to increase or decrease the torque produced by a motor to suit different applications. Remember, the length of a lever can increase or decrease the force on an object at the expense of the distance through which the lever must be pushed. Similarly, the torque produced by a motor can be increased or decreased through the use of gearing, as you know. So, an increase in torque comes with a proportional decrease in rotational speed. So, for example, the meshing of two gear teeth can be viewed as equivalent of the interaction of a pair of levers. So if you look at two gear teeth and the diameter of those two gear teeth and imagine those to be levers, you can often sort of display it or describe it like that. The use of adjustable gearing is obviously necessary to obtain good performance in vehicles powered by combustion engines. These engines produce maximum torque only for a narrow range of high rotational speeds. So, you know, adjustable gearing obviously allows sufficient torque to be delivered to the wheels at any given rotational speed of the engine. So there we go. Torque is not a force, at least not directly in itself, in its own thing. Torque, remember, torque is a measurement. It is a vector quantity. It is a result of. It is a measurement of, as just described. Use those words, and I think engineers would be much happier. And I know it sounds fussy, and it is fussy, but when you watch videos of people talking about this sort of thing, it really starts to grind your gears, because terminology is massively important for engineers. You can say to someone, oh, that material's really tough. Yeah, use that. You know, if they never tested it and the material wasn't tough but it was brittle, disaster. You know, the terminology is important because it defines the material, it defines everything about the properties of that thing. So, you know, torque, vector quantity, it's a measurement, it's relational, it's bidirectional, it's this, it's that, but it's not a force. Hopefully you'll all agree. Otherwise you can just leave your comments down below and I'll get back to them when I can. But thanks for watching another episode of Shed Talk. Really appreciate it. I'm going for a glass of wine and a sit down to edit. Cheers. Thanks very much. Bye.